Welcome to another deep dive. Today, we're tackling a concept that's, well, it's everywhere in our daily lives, but often feels a bit fuzzy. We're talking about electric power. You might have heard the term aka used in our source material, which is Korean. This deep dive is all about cutting through that complexity. We want to make sense of how electricity actually works for you, especially, if you're looking to understand it from the ground up. Our mission today, and we're guided by some really great insights from John Byung-Chil's book, Akanyoshe, that's published by Gilbert Publishing Her, is to really demystify electric power. Think of this as your intuitive guide, like a shortcut to understanding that little W you see on all your appliances. It's something we all use every single day, right? So if you've ever wondered what those numbers on your hairdryer or your fan truly mean, or maybe just how electricity performs its magic, well, you're definitely in the right place. Let's jump right in.
Okay, so we use tons of electronic products all the time, and they all perform some kind of work, right? But how do we actually put a number on that, on the work electricity is doing?
Yeah, that's the fundamental question. And what's essential here, especially if you're new to this, is that the way we quantify that work, well, that is electric power, the sort of engineering definition. It basically boils down to the amount of energy an electrical current uses, or the work it performs, every single second. It's what lets us put a number on what electricity is actually done.
Okay, let me see if I've got this. So it's not just about like turning something on. It's more about how much oomph it's putting out over time, like the rate it's doing the work.
Exactly. That's a great way to put it. The rate. You can think of electric power as a kind of force, maybe, or a measure of the power that electricity generates. The symbol we usually use is P for power, and its unit is W, which we read as watt. You see that everywhere. So a larger power value, a bigger W number, just means a greater force or a higher rate of energy use. And for really big numbers, we use kilowatts, kW. That's just 1,000 watts.
Right, kW. So, okay, when my fan says it consumes, say, 200 W, or maybe an iron uses 800 W, that's just telling us about the work or the force those things are exerting per second. But for us, the people actually using these devices, what does 200 W feel like? What does that really mean in our daily lives? Does it cost more?
That's a really good question. And this is where it gets, I think, really intuitive, especially for beginners. To make it feel more tangible, you could actually think of watts as a kind of, like agi currency. Think of it like money.
Money. Okay, intriguing. How does that work?
Well, for example, if a fan is 200 W, you can imagine it spending about 200 units of this energy currency every second. The source material we looked at is Korean, so it uses 1. You could picture like 201 worth of electricity being used each second. So if an iron is 800 W, it's using like 801 worth per second. Just a conceptual way, really, to grasp the relative cost or the usage rate of the power. It helps compare things.
Ah, okay. That money analogy actually makes it click instantly. I can see how that helps someone get a handle on the scale of things. So if watts are like money spent per second, does a higher wattage device just automatically cost more on my electricity bill then? Or is there another piece, maybe like how long I actually use it for?
Right. That's the crucial distinction. You've hit on it. Your bill depends on both the rate, the watts, and how long you use it. And thinking about the rate leads us to the more precise definition of power. While there are a few ways to define electric power, probably the easiest one to grasp is the formula. Power, voltage, H, current. And in Korean, from the source, that was power, voltage, H.
Okay. Power equals voltage times current. PAK is VXI. Got it.
Yeah. So let's put that into practice. There's an example in our source material. If a fan uses 200 volts, that's the V, and it has 1 ampere, that's the current flowing through it, then its power would be 200 V multiplied by 1A, which equals 200 W. So what that means is if you see an appliance rated at 200 W and you know the voltage is 200 V, then 1 amp of current must be flowing through it when it's running.
Right. Okay. That makes sense.
And we can apply this further. Let's say you have something consuming 1,000 W of power and it's plugged into a 200 V outlet. Well, that means 5 amperes of current must be flowing. You just divide the power by the voltage. 1,000 W divided by 200 V equals 5A.
Okay, I see how the math works.
And if we connect this to the bigger picture, like for your home, the voltage usually stays pretty constant, right? In many places, like Korea mentioned in the source, it's typically around 220 V. So if the voltage V is constant, then a larger power value, P, the wattage, must mean more current I is flowing. More power means more current, basically, when voltage is fixed.
Ah. So this means that for most of our homes, running on that standard 220 V, Just checking the wattage, that W number on our appliances, is a pretty direct way to know which ones are demanding more electricity at any given moment. You can literally just look at the numbers on your stuff, your appliances at home. And the one with the bigger power number is doing more work each second. It's spending more of that energy currency per second.
Exactly. That's the practical takeaway for comparing devices running side by side.
Okay, that makes perfect sense for understanding, like, consumption levels. But does all that electric power get used in the same way? I mean, does a fan use power the same way that, say, a toaster does? They do very different things.
That's a really insightful question. And no, it's not always used the same way. You're right, some electrical products consume power, mainly by generating heat. Think about things like electric irons or hair dryers, electric blankets, toasters. In those cases, basically, electrons are passing through something resistive in the circuit. They bump into atoms, lose electrical energy, and that energy turns into heat. There's actually a physics principle for this, Joule's law, that describes this heating effect.
Okay, so heat is one way, like my space heater.
Precisely.
Yeah.
But as you hinted, not all electrical products just convert power into heat. Think about fans or refrigerators, air conditioners. They primarily use electric power to, well, turn motors. They do mechanical work. They move air around, or they compress refrigerants to move heat around. It's about motion.
Ugh, that's a fascinating distinction. Heat versus motion. So it's not just how much power something uses, the wattage, but also how it's actually converting that electrical energy into something useful. That's actually a really useful way to think about it, especially when you consider what an appliance is for, or maybe even how efficient it is. Wow, okay. What a deep dive this has been into electric power. Feels much less fuzzy now. We started off just trying to figure out how to quantify electricity's work and learned that electric power, measured in watts, is the answer, it's the rate of doing work. And we used that really helpful money analogy to get an intuitive feel for it, especially, for beginners. Then we unpacked the actual formula. Power equals voltage times current. And we saw how that plays out with your home appliances, especially since the voltage is usually constant, like 220 V. And finally, we looked at the different ways that power gets used, sometimes as heat, other times to create motion.
Absolutely. And we tied this all together, understanding this concept of electric power, of wattage. It really does empower you. It lets you think more critically about energy use in your daily life. You can start to make sense of your electricity bill, maybe make more informed choices when you're buying new appliances. You can now look at that W on an appliance and immediately grasp its energy appetite, its rate of consumption.
That's brilliant. So maybe next time you're using an appliance, just take a quick peek at its power rating, the watts. You could even try imagining it in those money terms we talked about. Or just think, is this thing mainly heating up, or is it spinning a motor? And maybe ask yourself, what small change could understanding wattage help you make in your daily energy habits? Could it help save a bit of energy, or perhaps choose that next kettle or fan more wisely? Keep observing and keep learning.